Hello, gang. As you may have, if you've been following this project at all, you've noticed that I keep changing what I'm doing with the motors. And a lot of this has to do with my lack of knowledge when it comes to physics and mechanics. Basically, I'm a professional amateur and I learn as I go. Fortunately, there are people much smarter than me on the forums that help me through these areas of lack of knowledge. And one of those is Jeff Conter. He's in the UK, and he has helped me understand a little bit more when trying to describe his idea for a drive system, which is based on the is it an idea or is it a, I don't know what to call it exactly, the phenomenon of constant power. So in this video, I'm just going to go over what constant power is, how it would apply to Kinograph, and how it's different than what we've done before. I think I'm going to try to implement this setup and see how it goes. And mostly I'm recording this for my own future self, who will absolutely 100% forget all of this in a matter of days. So this one's for you, me. Okay, so we're headed towards an explanation of constant power and how it will apply to Kinograph. But in order to understand that, I think we should start off with something that's a little more common, and that is that most circuits that power drive systems are either constant voltage or constant current. You can think of this in terms of battery chargers. Depending on the type of battery, you either need to feed it constant voltage or constant current in order for it to recharge correctly. And those are the most common types of power circuits out there. And what they do is they monitor one or the other, and then they maintain the opposite of that so that you can always rely on it. So let's talking more drawing. Let's say I need to maintain a constant voltage over time. What I'm going to do is monitor where my voltage is at, and I'm going to adjust the current over time so that it remains constant. And how would this change over time? Well, imagine that there's a fluctuation in basically force. So if I'm a car and I need a constant voltage to this car for whatever reason for the circuit, the car can be going uphill and need more energy, or downhill and less energy, etc. So the work that is being done by this machine, we assume, is going to change over time. But we want to maintain constant voltage, so we measure the current, we adjust that on the fly so that we have something that is reliable. Now, what does this do for the power output? Output of power being watts, which is always in relationship to these two. It basically, you can just say, look, if I have the same amount of voltage and less current here than I do up here, well, volts more current, that's up. So it's basically going to follow this curve. And the whole point of this is one remains the same, two will change, and that all three are always in relationship to one another. Okay, let's talk about constant current, which will be very easy to understand now that we've gotten through the mess of one of these. So we have constant current. We are going to measure the current in the system and adjust the voltage as necessary. And because the relationship to volts and amps have not changed since we drew our last graph, when you have the same amount of amps and less volts versus the same amount of amps and more volts, the power graph is going to follow that as well. So one remains the same, two change, they all are in proportion to one another. And now for the grand finale, let's talk about constant power. So there's power over there. In this case, we have an input voltage, that's how these circuits are designed, that varies over time with the power that with the work that is required from the circuit. So in all the other cases, the first line we draw is sort of the input. What's the thing that we need to measure? And then what's the thing that we adjust on the fly? Now here's the interesting part. This is actually in direct opposition. So in order to get to the same watts, if I have more amps, then I need less volts. If I have less amps, I'm going to need more volts. So again, one stays the same, two change, but all in relationship to one another. This is the graph for constant power. Now let's talk about why this is a good idea for Kinograph in the next section. So how does this apply to the actual Kinograph setup? Well, let's start off with some simple equations. Torque, and this is for physics of a rotating body. Torque equals radius times force at the radius. And we're going to get to the diagram if that doesn't make sense yet. Power, or watts in our case, is equal to angular speed times torque. I guess when you're talking power, watts is in every case. So what does that mean? Let's simplify it. Let's substitute torque in the power equation for what's on its right side. So if we do that, we have power, or watts, is equal to angular speed times the radius times the force at the radius. Great. What do we do with that? Well, let's draw some circles and shapes and colors, and hopefully dumb me can figure out how to explain this in a way that makes sense to me and hopefully you. All right, the radius, I've got two different radii here. One represents the film at the beginning. This is the take-up side, so the right side of the scanner, or a cassette tape, or reel-to-reel tape, whatever. This applies to all of those things. And when we start off at small, when we get to the end of the reel, it's going to be big. So what direction is our force in? So if this is the film coming up, then imagine someone pulling on that black thread. That's going to mean that the force is in the opposite direction that we are winding in. So there's our force at the radius. So our force is counterclockwise, and the power that we are trying to give to this reel is going to be clockwise. We want to wind it up to the right against the force in the opposite direction. Okay, so let's borrow that equation. Let's move it down here, turn it blue, and try to simplify it. So if we talk about angular speed times the radius, remember going back, the radius starts off small and gets bigger, which means the angular speed, I should pause here and say, what we're after, the goal of this, is that the scanner scans at a constant frames per second. So let's say it's 12 frames per second. That means that whatever the angular speed is and the radius is, they need to figure out where they are over time in order to maintain a constant frames per second. And we might call that, looking down at the equation simplification, the speed of the scan over time. We want that to be constant. We want it to be 12 frames per second. So we want to decrease the angular speed as the radius increases, and we're calling that the speed of scan over time. The force at the radius, the pulling on the black string, we can call tension. And we're going to use that on the other side of this diagram for the feed reel. So let's try to, if you're confused, let's just go to the bottom of this blue equation and think of it in really simple terms. Power is equal to the speed of the scan over time, which we want to be constant, times the tension. So if we imagine that we have a constant tension, then we can kind of cross this out and say we don't have to calculate this because it's always going to be the same. Excuse me, and we're going to get to that. Just assume that that's true for now. Well, what we're left with is power equals speed of scan over time. Power is equal to the speed of scan over time, which should be constant. So when we're talking about constant power, what we're really saying is, am I going to change this? There it is. Constant power is in direct relationship to speed. In other words, if you change the output of the constant power circuit, you will be changing the speed of your scan. That's all we're saying. So how do you know what the speed of your scan is? Well, we need a feedback mechanism, and in this case, the easiest one we have is one that is already working for us, and that's the sensor that is calculating, or that is detecting the holes in the film, and provided we have a backup system for missing holes, which we do, it's a timer for now, then we can say, we know what the speed is, and we can adjust our constant power circuit accordingly. Now, when I say adjust, that could be a knob, or it could be a digital input, like a little interface. But it could also be an algorithm. It could be something that says, hey, what's our feedback on this? Let's adjust the output of that circuit accordingly so that we always adjust our speed. And that's what we really want. In other words, instead of turning a knob to constantly update the speed according to the feedback from the sensor, what we really want is a knob that says your target constant speed is 12 frames per second. Please do whatever is necessary to do that. My cat is crawling all over me. Okay, hopefully I haven't lost you yet. Let's talk about the other side. Let's make it green so that I don't forget that they're different. And, oh, that's not what I want. There we go. We're back. So same thing. The force is against the direction of rotation. We are coming off, we're feeding off the left side there towards the blue. And so that's the direction of our force. The blue is pulling from the green. So that's pulling against the radius there, and our motor is going to be opposing that force in a clockwise direction. Well, what is it up to? What's that motor up to? Cat, oh my gosh. I don't want to start this video over again, so I'm putting you away. Rejected. Make this green so I don't forget they're related. Same thing, exact copy over here, except we are going to assume this time that this is constant. We just talked about how that's going to remain constant with an algorithm and the feedback loop, etc. So we can assume that this is always going to be the same. So now we can reduce this on this side to say that given a constant speed, meaning that this is taken care of, power on this circuit to this motor should be equal to tension, which should be constant over time. And we need that to be constant so that this is true. And now you can see that these two are very much related to one another. If this is constant, tension, then we can assume this is true, that speed is true, which we need in order for tension to be true, which we need, and you just bounce back and forth. So these two are very much connected. And if to finish this out on this end, I guess I didn't finish it out. Or in another alternate timeline I did. We can copy this over. And as you can probably guess, it's going to say that the constant power from this circuit is responsible for tension. And for our feedback, we can't use the perf sensor here. We need to know what tension is on this. That's the thing that we're trying to get, not speed. And so something that might be good for that is just like a little strain gauge or a tension hub that you... God, cat! I hope you find this amusing, because I don't. In the film path is there, and I'm too lazy to re-record because I have so many other things to do. And then we're basically measuring force in this direction. I have some ideas about how to do that, or we could just use the tension hub that we used to have. So there you have it. That's how this would apply to, that's how we would apply constant power to the Kinograph. Oh my gosh, I need to end this video. And there you have it, more or less. He has found his spot. I know you've all been worried. Are you going to stay there? Nope. Gotta switch. Gotta change. Where are we going? Oh yeah, let's do that. That's wonderful. Oh my God, constant entertainment over here. All right, so that's the idea. What's next is, I don't know how to build this circuit. I've done some research. I'm gonna post that research in the forums. I'm talking to some independent contractors to see if they can do it. Jeff is working on his end, and eventually we'll come up with something. If you know how to do this, or you know someone who might, please point them towards the forum post. I'll put a link in the description, and we would love to have their help and expertise. Thanks for listening. I'm sure that was very nerdy.